Okay. Hi, everybody. Today, we're going to talk about decentralized coordination. And I'm going to go through a series of experiments that I've been doing. So let's start with this example. So this example was given to us as part of a fairly detailed evaluation that Denso did of Lingua Franca, where they were trying to apply it to a number of different contexts. And in this example, they raised a number of issues. And so I'd like to go through some of these because it's a really pretty classic example, but it's a distributed system where you've got some sensing, some computation, some actuation, and there could be pretty significant delays in this. For example, you might do these three things on three distinctly geographically separated platforms, and that will result in a kind of variety of unpredictable and uncontrollable delays. So one very concrete example would be where the compute gets done in the cloud. Okay, and imagine, for example, sensing being done on a vehicle, compute being done in the cloud, and actuation being done in a roadside unit. Okay, so these might be really quite distributed. Okay, so there's a few aspects to this. So this is pretty much how Denso constructed the application in the first place. They modeled some delay in the sensor, which might be because of doing some pre-filtering or something like that. Then they have a variable delay in the compute, and in their particular test case, it just alternated between taking 10 milliseconds to execute or taking 50 milliseconds to execute. And then in the actuator, they specified a deadline, which they wanted to react to actuation. And in addition, they used after delays on the communication between the components. And in this case, the after delays you can think of as implementing this principle that has come to be called in the literature system level logical execution time, or LET. The system level aspect of LET is referring particularly to distributed systems, and it broadens the idea of logical execution time to deal not just with execution time, but also with communication time, the time it takes to communicate. Okay, so one way to think of it is that these logical delays are trying to absorb the communication and computation delays and turn them into more predictable timing. Okay, so in particular, if the computation and communication for the sensor and the communication between the sensor and the compute is less than 15 milliseconds reliably, then the compute will be able to handle inputs on a very regular basis. Okay. The variability in the computation and the communication will be absorbed by this logical delay. So you could in principle get very predictable timing. Now, getting predictable timing with a compute function is really not interesting. Where you really want to get the predictable timing is in the actuation. So if you think of it, if the total delay, the total logical delay along this path is able to absorb all of the variability in the computation and communication, then the actuation time can become very regular. So you can put a very tight deadline on the actuation, and as long as the logical delays actually do absorb the full variability of the computation and communication, then actuation will occur at very precise times. Okay, so that the tight deadline is in effect specifying a requirement for the actuator to fire at 30 milliseconds greater than 0, 100 millisecond, 200 millisecond, et cetera. Okay. So that's the system level logical execution time principle. Now, in this case, so we're using decentralized coordination. All right. So one of the issues that the designer faces is that they have to choose um, uh, the STA and the STAA parameters. Okay. And in this case, those all default to 0. So if you don't specify an STA, which is a safe to advance offset, or an STAA, safe to assume absent, then they default to 0. So in the case of the sensor, having it default to 0, the STA default to 0 makes perfect sense because it doesn't have any inputs. So it only needs to look at its local event queue in order to determine whether it is safe to advance to the next logical time, right? So it's got a timer here. That's the only source of events. When it wants to advance to 100 millisecond, it should, by default, wait until physical time meets that 100 milliseconds. But once that has happened, it doesn't need to wait any further. It is safe to commit to the 100 millisecond advance. Now, the compute component also can safely advance its logical time because it has no local sources of events at all. So it won't be even attempting to advance its time unless it receives an input. And the presumption in Lingua Franca is that input channels are in order reliable delivery and that they arrive in timestamp order as well, that on any given channel, events will have monotonically increasing tags. And consequently, as soon as compute sees an input with a tag, it is safe to advance to that tag. So it can use an STA, a safe to advance offset of 0 as well. Similarly, with the actuator, it's got no local events, so it can use an STA of 0. So whenever you have such a chain of operations and everything depends on an input from a single source, then things are pretty straightforward and the defaults work. Okay. Now, one problem that Denso highlighted with this strategy is that the deadline violation handler here gets invoked only in reaction to an input having arrived. So in particular, this compute function here takes either 10 or 50 milliseconds. When it takes 50 milliseconds, the deadline is going to get violated. Okay, because the say it happens on the signal that's sent with originally with timestamp 100 milliseconds. The timestamp when it arrives here will be 130 milliseconds. Okay, but the physical time at which it arrives will be at least 115 plus 50, 165 milliseconds because of this 50 millisecond physical time delay. That's more than 5 milliseconds larger than the timestamp of 130 milliseconds, and consequently the deadline will be violated. But the deadline mishandler gets invoked rather late. It only gets invoked when the input arrives. Okay, so the question that Denso raised was, well, it sort of looks like that's a problem because we want to react to the fact that the deadline is going to be violated. We know it's going to be violated, and we want to react to it sooner, as soon as we know that it's going to be violated. So, so we looked at it and said, well, okay, you can do this in Lingua Franca. Here's how you do it. Okay, in the actuator, we again use a safe to advance of 0. Okay, and we have two distinct reactions now. One that we call the normal reaction. Okay, and what that'll do is simply actuate when things arrive on time. Okay, but that has a safe to assume absent offset of 5 milliseconds. So what happens now, oh, and there's a timer here. Okay. And notice that this timer is logically perfectly aligned with the timer in the sensor, plus the taking into account the communication latencies, right? So every event produced by this timer is guaranteed in this particular program to be logically simultaneous with an input. All right. So now, if you have a safe to assume absent offset of 5 milliseconds, what that means is, consider the event at 100 milliseconds. Okay. That'll have a timestamp of 130 milliseconds. If it hasn't arrived by physical time 135 milliseconds, okay, then it will be assumed absent because of this STAA. Once it's assumed absent, this reaction will not fire, all right, but this one will. So now the checker can determine, well, did in fact data arrive? So it uses a state variable to check that. So there's a state variable, data arrived. When normal data arrives on time, that state variable gets set to true. The checker resets that state variable to false. Okay. So even if the data has arrived, then the checker is happy. Data arrived on time, no problem. It doesn't have anything to do. But if data has not arrived, the checker can now react to the absence of data and, if in effect, deal with the deadline only 5 milliseconds after the data should have arrived. So now you can get a very tight reaction on the checker where it's reacting to the absence of data. Okay, so that 5 millisecond STAA puts a lower bound. You can also put a deadline on the checker, which then puts an upper bound. And so this says that you will react to the absence of data at the 130 millisecond timestamp data didn't arrive by 135. You invoke the checker. As long as you invoke the checker before 150, okay, then you don't violate this deadline and you can do some backup actuation. If you do violate this deadline as well, then what you're reacting to is a local problem. Okay, the checker didn't get invoked quickly enough, and there's two potential causes for that. One is that the actuator did get invoked and took too long to execute. So you can check to see if the actuator is taking too long using this deadline, right? Or the actuator did not get invoked and the runtime system failed to invoke the checker in time.
Edward, what I think also could work here is, instead of going via a state variable, is that you trigger reaction 2 also by this input port. And then instead of having the state variable, you basically just check if both, if the input is present basically as a condition, right? Then you can actually also get rid of the state variable. And then it's also basically this dependency is then also present inside your diagram.
Ah, very nice. Yes, that's a wonderful improvement. And that also makes the code clearer, right? Because it's literally just checking for the presence. Yeah. And it also makes another, feature of this that I find really quite interesting, and I think that is genuinely unique to Lingua Franca, right? This is relying on the fact that the tags of these events, these timer events, are exactly the same as the tags of the inputs. Okay? There's no fudging there. There's no round off errors. There's no, well, if they'll be close enough, or if the physical timing is, no, they're exactly the same numbers. Okay? And this whole strategy relies on that. And actually, so Tassilo's suggestion here would make that even clearer, right? Because the timer event, it will be logically simultaneous with the input. And if the input is absent, then you've missed, you're missing an input at the time, at the physical time that the checker gets invoked. Right? So let me just show you how this program works when we run it. So forgotten what I called it. I think distributed. Oops. So I've checked this into the playground, and I will update it with Tassilo's suggestion. So this is, oops.
I have a question.
Go ahead. I guess
if the STAA is different than 0, are we going to add the STAA plus STAA when checking?
That's a very good question. And one of the things to recognize is that the STAA is an offset relative to a logical time at which you can assume an input to be absent. Okay. But it's the offset is not just the number you give to the STAA. It's that number plus whatever your STAA is. Okay. And that'll become quite important in a later example, and it's a really subtle point, but we'll come back to that example, that question at that point. Okay, so when we run this, it starts up the 3 programs that it generated, and you can look at, so the first thing that happens is the sensor at logical time 0 produces an output. Compute then gets invoked at 15 milliseconds because of the after delay, okay, and does normal processing where it takes only 10 milliseconds to do that. And then the actuator gets invoked at 30 milliseconds, and that occurs at physical time that is 31.7 milliseconds. So this, you can see that the computation and communication time was largely absorbed by the logical delays. So in other words, the physical time at which the actuator gets invoked is fairly close to its logical time. It's within 5 milliseconds, and hence it meets its deadline. Okay? The checker then gets invoked and determines that data arrived on time. Okay? Then at the next 100 millisecond boundary, the sensor triggers again, compute triggers again, but takes a total of 50 milliseconds to execute. Now the checker is the next thing that gets invoked in the actuator. The reaction to the input does not get invoked because of the STAA offset. And it's getting invoked now just 5.8 milliseconds late. Okay, the STAA was 5 milliseconds, so that put a lower bound on that offset. That's within the 20 millisecond deadline of that reaction. So it handles, it actuates a backup actuation, right? So this is whatever it's going to do in the event that an input did not arrive on time, but it does it early. It does it close to the logical time at which it would have handled an input had it arrived normally. Okay, then the next thing that happens is the STAA violation handler triggers because the input does eventually arrive. And in this case, what the application does is it just drops the data. It says, this data is too late. I have no use for it. Okay, and then the process just repeats. All right, so one of the things that to me is very interesting about this is that it's a way of looking at real-time computing in a very different way from the classical way. Notice, we're not really emphasizing worst-case execution time. We're not saying a piece of software needs to finish by a particular time. We're also we're never referring to a global physical time. We're only ever referring to local physical times. Okay. The only global information is these logical times. So the fact that the logical time of this aligns perfectly with the logical time of the events that are a consequence of this, that is a global property, but the physical times are not. Okay, let's move to the next example. So this is in a different repo. This is actually now a regression test in the main Lingua Franca repo. And it's a variant of the ping pong regression test that was already in there. And this example came up because David Ching, who was an undergrad who was working with me last fall, was trying to port our benchmarks, the Savina benchmarks, to measure our performance with decentralized coordination. And he kept running into problems, and the problems had to do with a relative immaturity of the implementation of the decentralized coordinator, which identified a number of interesting corner cases, mostly having to do with the program starting and stopping, the startup execution and the termination. Okay, so let's just walk through what this program does first. So the conventional, the ping pong that was previously in the repo was simpler, right? It was just this. Okay, so that worked fine. But when David tried to replicate the structure that was used in the benchmarks, he started to run into problems. And so how does this work? Well, the start reactor here has a startup reaction that simply produces an output, which starts the ping pongs communicating. Okay, so the ping pong reaction will send its first output. The pong reaction will react to that, responding with a response here, and the response here will count to see how many responses it has had. And if it's not finished, then one logical, I think it uses, no, it uses a 10 millisecond offset in this case. So 10 milliseconds later, it sends another output. Okay, this would not be a good choice for a benchmark run because you wouldn't want this 10 millisecond lower bound, but it doesn't matter. Okay, when the ping reaction has found that it's received enough inputs, then it sends a finished signal to start, and then the start reactor calls request stop and brings the whole program to a termination, at which point the Pong reactor collects statistics, okay, and exits. So that's the design here. Now, one of the first things to notice is that there is a zero delay loop between these reactors, okay? And the reaction two is expecting a response from Pong. And in order to ensure that it gets that response, it uses an STAA of forever. All right. So this is an interesting choice. The STAA is 0. Okay. The STAA is forever. So what does that mean? Well, that means that ping can safely immediately commit to a logical time as soon as that logical time becomes available on its event queue. All right. So how's that going to occur? Well, there's three possible events that can cause ping to want to advance its logical time: an input from either input port or this logical action sitting on the event queue. Okay, those are the three possibilities. Initially, when it starts up, it doesn't have anything on its event queue at all. Okay, and one of the things that David discovered is that if it didn't have anything on its event queue initially, it would commit to tag 0, 0, discover that it had nothing to do, and then declare tag 0, 0 to be complete. And then it has an STA of 0 and an STAA and no STAA on the reaction to start. Notice there's nothing here. So it's an STAA of 0 as well. And consequently, it would assume that the input is absent because the start hasn't gotten around to sending it, and finish the execution at 0, 0. And then when it finally receives the start input, it would have a safe to process violation. And so David discovered that, well, the first thing that happened when he started up this program was he immediately got a safe to process violation that was unhandled because there's no safe to process violation handler specified here. All right. So that didn't work. Okay, initially.
So is the reason of that, is it due to the fact that the startup events are placed automatically on the pings event queue, but it doesn't for the subsequent events? For example, if start instead of driven by a startup is driven by a timer, this problem wouldn't occur for the subsequent events.
No, for the subsequent events. Yeah, this problem is really just a problem with startup.
Yeah, I see. Okay.
Although, no, not necessarily. If this were driven by a timer, the subsequent events, you would have to worry about whether there's a kind of a race now, whether you respond to the logical event before you've seen an input that might be simultaneous with it.
Mm-hmm.
So you could still have a problem even if this is a timer. But the first problem was really with the startup. And the problem was that every federate was actually completing its startup tag, even if it had no events at all to process in startup. So I changed this and said, okay, if there's no startup events, then don't commit to executing startup until you actually have an event to process. Okay. And only when you actually have some event to process, then you use the logical tag of that event and you advance to that. So that was the first change. Okay. Turned out that did not solve the problem either. Now, what happened was David discovered that he was getting a safe to process violation in the Pong reactor. Okay. Let me show you why that was occurring. Let me go over to right directory here. And I'm gonna compile this now with the old compiler, okay, before the fixes. What's the name of the program? Ping pong decoupled. Okay, so I've compiled this program. Now let's look at the result of the compilation. So if I go and find the fedgen directory, and let's look at Pong. Okay, so the way the compiler works with Federated is it splits out the Lingua Franca program into components, and it inserts this network receiver and network sender reactors. Okay, this one is a rather trivial reactor that is really all about just dealing with multi-ports. The Pong is the ordinary reactor that was there in the Federate originally. Okay, so why was there a safe to process violation? Well, look at the network receiver. it has a startup reaction in it. So at tag 00, this federate actually has an event to process. So it went ahead and processed it. Its STA is 0, its STAA is 0. So it went ahead and processed it and completed this startup reaction, then had nothing more to do. Then it received an input that wanted to be at tag 00, and that was a safe to process violation. So there was this hidden reaction to startup. And it turns out that the function that the reaction was performing was rather trivial. It was just initializing a field in a struct. So I changed this so that the code generator initializes this field instead of putting the initialization in a startup reaction. So now if you compile this same program with the current release, startup reaction goes away, and we have no safe to process violations when we run this program. Okay, so we can run it. You can see the pings and pongs got sent and received. No safe to process violations anywhere. Okay, so that was a kind of unexpected subtlety that required some changes. And the principle that it's following is that what the user sees, the reactions that the user sees, really should be the sum of all the reactions. That when the infrastructure puts stuff in, it shouldn't put stuff in at tags that the user doesn't know there's going to be any activity, right? And so you want to avoid those kinds of insertions of sort of random activities inserted by the infrastructure, because they're going to affect how you deal with the STA and STAA. Now, I meant to change this guy also. This actually does have a STAA that.
So Edward, this basically, but the takeaway here is that basically then this kind of design, right? The design of the federated in current reactor C is fundamentally flawed in the sense that you cannot, for example, right, you need to have like a startup reaction to open, I don't know, your TCP/IP socket and so on, right?
Mm-hmm.
Right. Okay.
Yeah. Right.
And which is of course like in reactor micro CV, basically, it's basically part of the infrastructure.
Yeah, but I'm one of the things that I'm building up to is that right now the STA and the STAA are constants that are that you set them and they hold for the entire execution of the program. But that's often not what you want, right? So you might want at some tags to have an STA be one thing and a different tag be something else. And I have a concrete example of that, which I'll get to in a minute. But I also wanted to mention that, notice I just changed this STA from 1 hour to forever. And the reason that it was 1 hour is that another bug that I found is that if you set it to forever, there was a place in the code where there was an addition being done to that tag with no guard against overflow. And so the forever tag was getting a number added to it, and it was wrapping around and becoming a large negative number. And as a consequence, that always had the effect of having an STAA of 0. And it was very puzzling. We were scratching our heads for a long time trying to figure out why is this ignoring our STAA of forever. So you really, when you do arithmetic on tags, you should use the library functions provided to do that arithmetic. And this is probably something we need to do kind of an audit of reactor micro-C to make sure that everywhere that tags are manipulated arithmetically, that they're done so in a way that takes into account overflow possibilities. I assume you guys have been pretty careful with that, but it might be worth doing an audit of it. Yeah. Okay. Oh, yeah, there was one other point that I wanted to make, which is an even more subtle one. So let's look at what this finish reaction does. So first of all, the start has an STA of 0, and it doesn't specify any STAAs on any of the reactions. Okay. So what does that mean? Well, it has only a single local event source, right, which is going to trigger at tag 00, and it'll immediately commit to that and immediately process this reaction. So far, no problem. That's the first reaction. Then it goes to the second reaction and says, well, is there an input? And it says, well, the STA and STAA are both 0, so I can assume that the input is absent. So then it completes the 00 processing with an absent input. Okay. Then it has nothing to do. There's nothing on the event queue, so it doesn't even attempt to advance its tag until an input arrives, and then its tag gets put on the event queue. Then Start says, all right, it's safe to advance to that tag. It advances to that tag, and then it requests a stop. Okay. Now, what does the request stop do? Well, that broadcasts a message to the other federates and says, I would like you to stop, ideally at the earliest possible tag, no less than the tag that I provide. Okay, so the tag of the arrival of the finish signal gets broadcast to the other guys. The other guys all respond saying, yeah, okay, I can stop at this tag, which will be, in practice, it's non-deterministic which tag you'll stop at, but because of the timing, the spacing of events is big enough here, it tends to stop 1 microstep after receiving the finish signal. Okay? So then what happens? Well, now all 3 of these guys have an event 1 microstep later than the tag of this input. Okay? But some of these guys have STAAs of forever on their inputs. So now they try to process the finish tag 1 microstep later, and they go to the point where it has to decide whether to invoke this reaction at that tag. It says, well, I don't know the status of the input at this tag, and my STAA is forever. Let me wait. And so at the execution of the shutdown tag, ping just hangs and never exits. So the program, the overall federated program, fails to shut down. Okay, ping hangs, waiting for inputs, which it's never going to receive because Pong's not going to send any inputs. Now, Pong could send an output in reaction to its own shutdown. Okay, and that would unblock ping, but that's logically kind of a hack, right? So this is sort of the start of the next kind of big topic here, which is maybe STAAs and STAs shouldn't be constants that are the same throughout the execution of the program. Maybe they need to be variable. And so what is committed now in Lingua Franca is that at the shutdown tag, if the shutdown tag is the result of a request stop as opposed to a timeout, okay, then the assumption is that this is an asynchronous event that is unpredicted, okay? And that consequently, whatever values of STA and STAA the components assumed no longer hold, because this is occurring at a tag that none of them expected to be executing at. All right. So what the current runtime does is just reset these values to 0 for that particular tag. Perhaps not the most elegant solution. It has a consequence, right? It means that Kong should, in fact, not send an output in reaction to a shutdown, because that output will not be reliably received by the destination. Okay, because the destination may shut down before it even gets that that input, because its STAA gets reset to 0. But that at least allows the Federation to shut down and actually exit properly. I'm not convinced that that's really a good solution. Okay, I mean, another solution would be to have a reaction to shutdown in ping that explicitly sets the STAA to 0. Okay, but that requires a lot of sophistication in the user. So I decided that it was probably better for the user to tell them a simple rule. And it's a rule that the validator can check. Don't send an output in reaction to shutdown. Okay, I think that currently the validator does not check this, but just verify that. Yeah, the validator is allowing it. So I need to make a mental note that we should change this so that the validator does not allow that in the current implementation. Okay, so that's a real significant subtlety. All right, now let's zero in on this question of variable STAs and STAAs. So I created a sequence of examples, right, that that kind of illustrate interesting points about this. So this first one is a very simple situation where it's perfectly safe to have an STA and an STAA of 0 in the downstream reactor. There's no startup issues. There's no shutdown issues. This guy is going to react only to inputs. It's not going to have anything to do at any other time, so it never has to assume the input is absent. Okay? So no problem. This one is where you start to get problems, right? Setting STA and STAA to 0 doesn't work in this case, okay? Because what's going to happen, very likely the downstream guy is going to go ahead and advance, commit to this logical time, assume the input is absent, not execute this guy, and then execute this guy. And then it's going to later receive something from the upstream with the same tag and get a safe to process violation. Right? So we've seen that before. So here's a third variant, okay, which fixes that problem. You just have to set the STAA, okay, for this reaction to some reasonable number. And if you set it to forever, then you're going to get a data flow style, right? The choice between a finite number and forever here is about exception handling, right? And the way to think about it is that if your program is such that a failure of a message to arrive from upstream is a failure of the whole system, then you can use forever. Okay? If, on the other hand, a failure of an input to arrive is going to be treated just as a failure of the upstream or the network, then you should use a finite number for this STAA, and then this is your exception handler. This code will get invoked if either the network fails or the upstream fails. Okay, so hopefully that's clear how you make that choice. When do you use forever? When do you use a finite number? You need to have a fault model in order to make that choice. Okay, let's look at a slightly more interesting example.
Excuse me, Edward.
Mm-hmm.
I think there's something I missed. So if downstream, the reaction one of downstream has an STAA of forever, this means that it will be always delaying reaction to if there's no input, right? Is this correct?
Yes, so they're very good question. Thanks, Chadlia, for saying that. So when you specify an STAA here, okay, the 20 millisecond wait will only occur if there is no input. Okay, if an input arrives, it doesn't necessarily wait the 20 milliseconds. As soon as it's got an input that has a tag equal to or greater than the tag that it's trying to commit to or that it's trying to process, then it'll proceed. Okay, but it will wait 20 milliseconds if the input is absent. Right? Was that your question?
Does this mean that if we have, let's say we have n reactions, then in a reactor, we'd rather have the lowest priority or lowest level reaction, the only one allowed to have an STAA of forever.
Oh, no.
Otherwise,
no.
So,
So the STAA is always relative to the tag. Okay, so if you have two reactions, if this second reaction was also reacting to the input and had an STAA of 20 milliseconds, that doesn't add an additional 20 milliseconds to the wait. Okay, it's going to be the same 20 milliseconds. So if this guy waits 20 milliseconds and the input and assumes the input is absent, and this guy is reacting to the same input with also an STAA of 20 milliseconds, it'll immediately assume the input is absent.
yeah, but if it's forever, then reaction 2 cannot execute.
That's true. If reaction 2 has forever, then reaction 2 will block.
So if reaction 1 has forever, then reaction 2 will block.
Yes.
Is this correct?
Yes, that's correct.
Does it make, won't it be safer if we warn the user about such pattern, because it's kind of
yes. I mean, this is why I said you need to have a fault model in mind, right? So you should use forever only in situations where a failure of a message to arrive is a failure of the entire system.
Thank you. I
right?
see. Thank you.
Only in that circumstance is that a legitimate choice. Okay, so this has an STA of 0 and an STA of 20. What if we reverse those and use STA of 20 and STA of 0? Okay. So it turns out that for this particular case, this really doesn't make any difference, even at the startup tag. Okay. Because at the startup tag, the STA is ignored, right? Because it's always safe to advance to 0, 0, right? STA means wait this amount of time before committing to this tag. Okay. And if you have an event at 0, 0, you can commit to the tag at 0, 0. Okay. The STAA of 0 here doesn't hurt you, however. You don't immediately assume that the input is absent, because the semantics is that the amount of time that you wait before assuming that the input is absent is the sum of these two relative to the tag. It's not you start at a certain physical time and wait that amount. No, you wait until physical time matches the tag you've committed to plus this offset. And the offset is always the sum of these two. It's a very subtle point, right? But it means that this variant works fine, right? It will wait 20 milliseconds before assuming that this is absent, even at tag 00. Okay. Now let's look at a little more complicated example. Whoops. So this one has much faster reactions downstream. So every 10 milliseconds, it's trying to react, but it only receives inputs every 100 milliseconds. So what's going to happen in the intervening example? So this one is worth running. Let me see. This is in the playground. Which one is this? Conditional A5. So let's look at, so at tag 00, downstream received an input at basically 16 milliseconds. So there's a 10 millisecond wait here, and then some overhead. Okay, and downstream received an input at 15 milliseconds, which was within the 20 milliseconds to assume absent. So, okay, so that was fine. Then it reacts to the timer, also at 16 milliseconds, okay? But now, at this 10 millisecond boundary, it reacts to the timer, but it reacts to the timer quite late, right? This is 30 milliseconds versus 10 milliseconds. So it's more than 20 milliseconds later than the timer. Where does that 20 millisecond offset come from? Similarly, the timer reacts to this 20 millisecond tick at 42 milliseconds. It reacts to the 30 millisecond tick at 51 milliseconds. Why is that? Well, it's because of this STAA,
Yes.
right? But the designer of this program knows that these events are not going to be present at these tags. So it turns out that we have an API for dealing with this that we haven't really made any use of, okay, where we can just vary the STAA. So let's have a look at how this downstream is designed. So the STAA is set to 20 milliseconds initially. So this is what will be in place at the 00 tag. But then when it reacts to an input, it sets the STA to 0 and starts a counter. So now at the next tag that it has on its events queue, which is at 10 milliseconds, now the STA is actually 0. So it immediately advances to 10 milliseconds and processes the timer. Okay, the timer increments the counter. And when the counter hits 10, it resets the STA to 20 milliseconds, which is the next, it knows that at the next tag, it's going to expect an input. So at the next tag, it'll actually wait 20 milliseconds for an input. So if I compile this guy, 6, look at it. So now you can see it reacted to the 10 millisecond timer tag at 17. Why 17? Well, because it's got an accumulated delay from the first 20 millisecond wait. But then subsequently, it's reacting really quite quickly. It reacts to the 20 millisecond tick of the timer at, wow, only 67 microseconds after the timer. That's really fast, right? The 30 millisecond tick at 31 milliseconds, 40 millisecond tick at 41 milliseconds. Only when it gets to the next time that there's going to be an input does it now handle the timer with some physical delay that's going to be at least 10 milliseconds. And in this case, it was very close to 10 milliseconds because of the 10 millisecond computation delay in here. So the challenge problem here, which I think is really pretty interesting, is that we can make the STA and possibly the STAA variable. We don't have an API for doing the STAA right now to make that variable, but we do have an API in Reactor C for making the STA variable. The high order bit here is that varying this at runtime seems like a potentially very interesting thing to do. For this particular case, because everything is periodic, you could synthesize automatically the variation that works. So the issue is that on the off cycles, you actually want both of these to be 0 in order to get the quick responses to the timer.
I guess we can use some static analysis to let STA only kick in when we expect some event, right? Because in this case, everything is static. So we know that the next event is going to come at t equals 100.
Right.
And we only block then instead of blocking at t equals 20 milliseconds.
Right. Now, I think that what we're doing in Reactor Micro C is actually accomplishing that because I think there is a communication of event queue information, right? Is that we've talked about doing that at least? I don't know if we've done that.
Yeah, we basically, this is definitely on the agenda that we basically can then, we basically want to support different coordination schemes on connections. For example, sending the next event tag, or alternatively, for example, a request response pattern where you can fetch, basically the downstream can fetch like, what's your next thing? And yeah, this is basically on our roadmap that you then can, I don't know, build like tighter couplings if you desire so.
Right. So we've run over time. I apologize. We should probably stop here.